All right. We are very excited to have Jeff Clune here today. Jeff is a professor of computer science at the University of British Columbia and a Canada CFAR AI chair at the Vector Institute. Um, Jeff has done a lot of amazing work and a lot of fundamental work in deep learning and deep reinforcement learning, and has extensive experience in academia and industry, including uh, spending time at OpenAI as a research manager and being a senior research manager and the founding member of Uber AI Labs. He founded a company that was acquired by Uber, and we are just very excited to have him here and hear about the latest amazing work that he's doing on agentic optimization and in the era of LLMs and foundation models. So, Jeff, thanks for being here, and I let you take it from here.
My pleasure. Can you let me know how questions? First of all, it's nice to see you, Azalea. Thanks for the invitation, and to both of the instructors. If people have questions, can they just speak up, or do you want to repeat them to me, or how might that work?
We will repeat them to you. Yeah.
All right. Well, then
Is that okay? Would that work?
totally fine. Yeah, actually, hello everyone in the class. I can't see you, but nice to be here. Fun fact, this is actually my second guest lecture at Stanford. I gave a lecture in Chelsea Finn's meta learning class a few years ago when I was at Uber. So it's great to be back, this time virtually. And this is a long class session, and I know that these long classes, they can drag on a little bit. So I think the thing that will make it the most interesting is if you have questions, please do ask them as we go. As you just heard, one of the instructors can kind of relay your question to me. So just raise your hand and they can let me know that I should pause. And I'm happy to answer questions as we go. And if it's taking, if I think it's going to derail us time-wise, I will let you know. But otherwise, I think it's probably more important to be interesting to you than to like blaze through all of my material. So with that said, I'm going to share my screen. And can somebody let me know if you can see my screen?
Yes, we can see it.
Great. And can you see my mouse cursor as well?
Yes.
Perfect. All right, here we go. So today I want to talk to you about open-ended agent learning in the era of foundation models. And this is going to involve covering a lot of different projects that I've worked on throughout my career. So it's a bit of a fire hose and a whirlwind tour, but please do stop and ask questions if you have them. But the main thing I want to do is try to introduce you to three classes of algorithms that are related that you may not have heard a lot about before that I think you might find interesting. They're called quality diversity, open-ended, and AI generating algorithms. And then I want to talk about how they can be used to make lots of cool things, including agents, the theme of this class, and how we're kind of in this new era where those algorithms are being fueled by and serving as the catalyst for they're being fueled by and being catalyzed by foundation models. And so the foundation models, like in so many areas, are really making everything easier and speeding things up and creating exciting opportunities. So before I even begin, though, I want to quickly talk about AI safety real fast. I think this is a really important topic. It's one that I lose a lot of sleep over and I've done research and published on. I take it really seriously. I've written this article with Yashua and Jeff Hinton and many others about managing AI risks. I think there's some unique safety issues to the kind of work that I'm going to talk to you about today. And here are some papers if you're interested in learning more. But I just want to start by saying I think this is really important. We have to proceed cautiously and wisely and prioritize safely. This talk is not about AI safety. That would be the focus of an entire other talk. But just know that it's in the back of my mind in everything that I do and the work that we did here. We did take a lot of safety precautions, some of which I'll mention. Okay, so I want to start with a paradox, which is that and this is true in life in general, if you try too hard to solve a problem, you will fail. But if you ignore the objective, you're much more likely to succeed. Now, this is only true of really hard problems. But as a metaphor for that, imagine you're in this maze here, and you start here, and you reward an agent or you reward a human for getting closer to the goal. Well, if you do that, we did that with an optimization algorithm. Actually, this isn't my work. This is Ken and Joel. But if you do that, the agent will go north to close the distance to the goal, and then it will bang its head against this wall pretty much forever. And it will never learn to solve this problem. In contrast, if you just encourage the agent to go explore, it will eventually trivially solve this simple maze. Now, you might think that that is overly simplistic and not true, but if you actually think about how science and technology work, you'll see that this is everywhere. For example, if you went back thousands of years to the time of cooking over fires and you said, I am the queen of a queendom and I will only fund scientists in my queendom that improve the ability to cook fast with less smoke, you would never invent the microwave because to do that, you had to have been working on radar technology and realize that a chocolate bar melted in your pocket. Similarly, if you went back to the time of the abacus and you said, I will only fund people who give me more compute per dollar per second, you would never invent the modern computer. Because to be doing that, you had to have been working on vacuum tubes and electricity. And those technologies were not invented because they might be useful for computation. So you wouldn't have produced them. So the conjecture is that the only way to solve really hard problems is by creating problems as you go without a long-term goal in mind, and then goal switching between them. And goal switching is this concept we introduced in 2016. The idea here is, hey, I'm working on problem A. I think I'm trying to make progress on it, like a roboticist trying to make bipedal locomotion, for example. But if I suddenly start seeing progress on a different front, like my robot starts crawling on all four legs or balancing on one leg, for example, don't throw out that interesting thing because it doesn't measurably improve your progress on the original problem. Instead, say, huh, that's interesting, or that's funny. I wonder if I could get better at that interesting task. And start practicing, optimizing, and getting better at that task also while continuing to work on problem A. So you're willing to kind of switch some of your focus over to something else. And scientific communities do this all the time. And we want our algorithms to act like a scientific community or an individual scientist and capture serendipitous discoveries. So that brings us to this class of algorithms called quality diversity algorithms. The idea here is that they will produce a diverse set of high-performing agents or policies. Just like natural evolution produced all of these crazy, but yet really interesting and really high-performing creatures that are all good at whatever it is that they do. And so the most popular algorithm in this field was one that I co-invented with Jean-Baptiste Moret in 2025 called Map Elites. And the acronym is a bit of a mouthful, but the basic idea is we're going to pick dimensions of variation that we care about. In this case, in this little toy example, the height and the weight of a robot. And we also have some notion of performance. Here it's going to be the speed of the robot. And then what we want is to basically come up with the best possible robots of every possible height and weight. So to do that, we're going to discretize these spaces of these dimensions of variation we chose, height and weight, and then we're going to run a really simple loop. First, we have to initialize it. So we'll generate a random agent. In this case, a parameter vector defines the robot's body and its policy, maybe its speed. You then evaluate the agent, see which cell it's in, and put it in there. Then you just run this loop. Take something out of the archive, perturb it a little bit, and then reevaluate that thing, see what cell it goes into. And if it's the highest performing thing you've ever seen in that cell, keep it. And that's it. Run that loop forever. And in contrast to traditional RL or traditional optimization, which will give you one solution, or the best solution it finds, this algorithm will return an entire set of solutions that teach you a lot about your landscape. In fact, we almost call them illumination algorithms as a community because they illuminate the search space. And I want to show you an example. So I had been working on soft robots for a little while, and we produced this menagerie of cool soft robots. But this was with evolutionary algorithms, and the trick is that every single run was pretty convergent and only had very slight variations on one type. The only way to get diversity was to run it multiple times and then collect and cherry pick examples from different runs. Also, the algorithm was almost never playing with this dark blue material, which I really wanted it to. So what we did is we said, let's try map elites on this. So classic optimization here, you can see doesn't perform very well. The dots are all black. If you add diversity, which we've been doing for decades, in this exact same search space of these two dimensions, the performance goes up. You get some yellow stuff. But look how little it explored the space, even though we were encouraging diversity explicitly, because it had to trade diversity off with performance, and it didn't want to give entirely up on performance, etc. Map elites, in contrast, with the same amount of compute, is a total sea change in terms of what is possible. Look at all the different stuff it taught us about the search space. There's a lot of optima over here. There's a little pocket of local optima over here. Really hard to do well up in this part of the space, etc. What's also really fascinating is that if you go to a final solution, because like for example, this is the start and I think it ends up right here. Take the final solution in one cell and say, where was all the search of its ancestors? Like where were the things that preceded that final solution? And the answer is it's not like nearby that space, but it took this long circuitous path through the search space that ultimately found its way here to solve this problem. So you would have to know ahead of time, if I want to get a good thing here, I have to somehow incentivize this crazy circuitous path through the search space. There's no way you're going to intuit that ahead of time. Just like you wouldn't have intuited how to get to a microwave or a computer thousands of years ahead of time. And so we use these ideas in this paper we had in Nature in 2015. You can see the map leads grid here on the bottom. And this is a robot that ahead of time in simulation will learn a bunch of different ways to walk. And then once it becomes damaged, will quickly search through the space of really high quality diverse gates that it found in simulation to find one that still works despite the damage and in the real world. And we showed that that worked quite well. 6 years later, we had another paper in Nature called Go Explore that applied this exact same paradigm, but this time to the problem of hard exploration problems in reinforcement learning. So those are problems for which you get very sparse rewards. So you have to take a whole lot of actions before you get any reward. For example, in this game, Montezuma's Revenge. At the time, this game had become kind of a mini grand challenge in the field because all of the current RL algorithms pretty much failed on it, despite a lot of people trying to solve it. In fact, you can see all those blue dots down here. Here's prior work, some of which explicitly was focused on trying to solve this game and not getting very far. And you can see this massive leap in performance. Once you basically apply the paradigm, that all we want to do is collect a lot of high quality yet diverse ways to get to different places in this game. And if you do that, you kind of blow the roof off of this game and you ended up solving this particular kind of open challenge in the field at the time. Furthermore, we use the same algorithm to go and apply it to all of the games in the Atari benchmark. And I don't know, many of you might not even remember, it might be getting a little dated, but the Atari benchmark was kind of the benchmark in the field of RL for a very, very long time. And this algorithm solved all of the games, which was a testament, I think, to the power of these ideas of quality diversity algorithms. So this is an algorithm called Go Explore that you can look into more if you are curious. It also solves really hard exploration problems here in robotics. So here's Go Explore in blue. This robot has to put its toys away and it only gets a reward if it puts the toy in one of these bins. And in all four problems, Go Explore solves it trivially. An intrinsically motivated PPO, which is kind of like the state-of-the-art approach you'd reach for if you weren't going to use Go Explore, doesn't solve these problems at all. It failed in every single case. All right, so I hope I've kind of at least whet your appetite that QD algorithms are worth looking into. And that's because they produce a diverse set of high-performing agents or policies. They harness goal switching and therefore provide a really good exploration of the space. So what's missing? Well, the most important thing is they're just stuck in one particular environment. And that's not their fault. That's pretty much true of all machine learning for the most part. We tend to pick a problem, or at least we did when we started this work, like Go or chess or Dota or StarCraft, and then we would work really hard on that problem, solve it, and then we'd move on to the next problem. But if you think about nature and what inspires me, I want an algorithm that will be what we call an open-ended algorithm. That is to say, we want an algorithm that will literally innovate forever. No matter how long you run this thing, it will continue to delight and surprise, be satisfy your curiosity, provide innovations, etc. Now, to date, we only know of two open-ended algorithms. One of them is natural evolution, which produced all of the amazing engineering marvels you see in the tree of life, such as jaguars and hawks and the human brain. And the other one is human culture. So ever since it's been running, human culture has not run out of ideas. It hasn't run out of problems to solve. Science hasn't converged. In fact, it's diverging. The more things we solve, the more tools we have, the more questions we have to further the process of going and getting more technology and answering more and more questions. So as my friend Jean-Baptiste Moret framed it so beautifully, could we create an algorithm that would be worth running for 1 billion years? And you'd want to actually come back and see how it is doing throughout that journey. When I started in this field about 15, 20 years ago, we didn't have algorithms that were worth running for more than about a couple hours. And throughout my career, it's gone from days to weeks. And now I think it's pretty clear we have algorithms that are worth running for a few months. But that's about it. We don't have things yet that would run for a billion years, let alone even for many years. And that's a North Star for the field of open-endedness, and I think for the field of computer science in general. So one of the things that I think serves as the rocket fuel for open-ended algorithms is that they generate their own problems, and then the solution to those problems opens up new opportunities and new problems to be solved. So, for example, evolution arguably invented the problem or the opportunity of leaves high up in trees, and the solution to those problems in the form of giraffes and caterpillar. And those solutions themselves now open up new niches. So things can live inside of giraffes or caterpillars, can cooperate with them, can eat them and prey upon them, it's all, et cetera, et cetera. So one of the first algorithms that we had where we really tried to go after this idea of automatically generating niches and problems and opportunities in an algorithm forever is work that we did at Uber called the Paired Open-Ended Trailblazer with these wonderful co-authors. And the idea here is to endlessly generate increasingly complex and diverse learning environments and their solutions. And the way that POET works is we're going to have a parameter vector that encodes environments, and we're going to be searching for environments. And then we'll periodically generate new environments and we'll add them to the population if and only if they're not too easy and not too hard for the current set of agents. In this case, it was a population of agents. It could be a single agent. And also if the environment is different than what we've had in there before. And then while we're doing that, we'll be optimizing an agent to solve each of these challenges. And critically, we allow goal switching. So as the set of environments grows, if something is working on environment 42 and it comes up with an innovation that makes it suddenly the best thing we've ever seen on environment 55, we'll basically copy an agent over into 55 and let it work on 55, while the original one is still working on agent 43 or environment 43. And so you allow goal switching, just like scientists and ideas can move amongst different academic communities and environments can move amongst niches. So in this work, this is pretty much the first work that I'm aware of that really tried to parameterize the environment and automatically generate environments. And it did this, and everything that you're seeing here is automatically generated by the system itself and then also solved by the system. So there's a neural net policy controlling the robot, and it has to tackle these increasingly hard challenges. And I don't know if you remember, but at the beginning of this video, the challenges were quite simple. Toward the end of the video, it's now mixing up harder and harder challenges, taller stumps, more rugged terrain, bigger gaps, and it's putting them all together until it's really pushing the limits of this little simulated body and doing about as hard as of an environment as we think this body and the physics of this system will allow it to. Now, interestingly, to test this hypothesis that you need goal switching, we went back and we took a lot of the final environments that POET had gotten these performances on, and then we said, all right, what if we didn't have a curriculum of goal switching and a big set of environments? What if we directly optimize with the same learning algorithm to try to solve this environment and this environment and this environment? Well, in every single case, direct optimization failed. Okay, it needed that curriculum to be able to get up to solve these really hard environments. Now you might say that's not fair. Like I'm familiar with curricula. Maybe you could invent a hand-coded curricula that is a kind of a straight path that linearly interpolates between the simple environment and the hard environment in parameter vector space and try to walk that line. We tried that, and in every case that also fails. So basically we don't know of another way to solve these problems except let an open-ended algorithm go and learn to solve them. This is a slightly like a follow-up paper where we had a different encoding, but all of these environments were produced and solved by the system itself, which is pretty cool. And that leads us to this. This is one of my favorite plots in my entire scientific career. Ever since I was a brand new grad student in 2003, I've been trying to produce this, which is effectively a tree of life, but one that has sustained deep branches where you get animals and fungi, and you get like the big cats and the dogs and the whales and the dinosaurs and all these things where the open-ended algorithm would riff on a theme and kind of continue to explore in this direction and this direction and this direction, a lot of diversity of high quality solutions. And this is an example of environments in POET, and we saw that signature of an open-ended algorithm, which is kind of deep sustained branches in a tree of life. Somebody took basically the ideas of POET and did it in a simulation and then just transferred it to reality. Effectively, Poet is really good at domain randomization, but it's not a manual version of domain randomization. It's automatically creating the challenges on the fly, tuning them to the current skills of the agent, and it worked quite well on this real robot transferred into reality, which was cool to see. So I hope Poet has shown you once again the benefits of quality diversity ideas, and now adding in the idea of generating challenges while we solve them in a never-ending loop. So that's the pro of Poet. The con is it's still kind of trapped in this small, simple space of 2D obstacle course environments, and we want to move beyond that. So I'm going to return to that in a little bit. But for right now, I want to zoom way out 30,000 feet and take a gander at the overall goals of our field. So many people in our field are motivated by making artificial general intelligence, ASI, human level AI, whatever name you prefer. If we should make it, and that's a subject for a different conversation, different talk, then I think you'd agree we still have a long way to go, although less so with each passing month, it seems. But I think it's really worth it to say, like, how will we get all the way to the finish line rather than just to the
Jeff,
idea. Go ahead.
let's open up for questions when you finish this.
So, how fast can I fly through these slides? We're talking about AI generating, actually, we're talking about producing AGI. And I want to point out something that may be obvious to everyone in the room, but certainly wasn't when I started making these slides. But maybe it's still not obvious to people, because I see people not act in this way almost every week. There's a clear trend in machine learning, which is that hand-designed pipelines are ultimately outperformed by learned solutions. And we've seen that with features like in deep learning and NLP, architectures, hyperparameters and data augmentation, and RL algorithms themselves. That was the subject of Chelsea's meta learning class. And so that suggests an alternate path to reaching our most ambitious objective of AGI, which is let's learn the entire solution. That might require lots of pre-training to ultimately produce a sample-efficient, intelligent agent. And we have an existence proof of that, which is Earth. On Earth, we had a planet-sized computer, 3.5 billion years of evolution, and it produced you. And you're the most impressive learning agent we know of in the universe so far. And so if we want to make progress on these kind of algorithms, which I call AI generating algorithms, we have to simultaneously push on three pillars. We have to meta learn the architectures, which is not done a lot these days. We have to meta learn the learning algorithms themselves, like in meta learning, and we have to automatically generate the learning environments and challenges themselves, which nowadays goes by the term of creating synthetic data. Handcrafting each of these is slow and limited by our intelligence and time, and so it's better to let machine learning do the heavy lifting, plus a lot of compute. So far, I've introduced many algorithms that I think will help a lot with pillar 3, such as QD algorithms, open-ended algorithms such as Poet. I'm going to tell you about some more. But what I want to pivot to now is that kind of sets the table for the rest of the talk, where I want to say, how has all that work, which I've been doing with my collaborators for a decade or more, how has it now been turbocharged by foundation models? And I think there's many, many ways in which it has been changed. So the first thing I want to mention is this OMNI work that I alluded to earlier. And this has been done by Jenny Zhang here in my lab at UBC, who's wonderful. And it's called Open-Endedness via Models of Human Notions of Interestingness, with Joel and Ken as well. So the idea is that if we want to produce a truly open-ended algorithm that we would want to run for 1 billion years, we need a really vast search space, basically any possible environment. And so you could imagine, for example, any task that is just describable by words. And this is getting to the question that was just asked. The problem is if you allow any possible task, then many of the tasks are impossible, or they're nonsense, they're too hard, or they're too easy. So what we want is that the tasks are both new and interesting. And how do we find them? Well, the first challenge is we want them to not be too easy and too hard. We can use learning progress, which is a technique that I and others have used for a long time before. But there's a problem, which is that you can have infinite learning progress, which means you can always learn new stuff on a particular problem, but that problem might not be interestingly different. For example, if I pick a random irrational number like pi, and I tell you to memorize the first couple of digits, and you do, and then I tell you and you tack on a couple more digits and you memorize those, well, there was some extra learning progress for you. But if I keep doing that over and over and over again, that 700th time I tack on a couple extra digits of pi, it's no longer an interesting form of learning. You're learning, but it's not an interestingly different problem to what you already know how to do. And so what we need is an automatic way to determine what is interesting and new in addition to learnable. Now, for decades, people have tried to quantify what constitutes something that is interesting. And then the problem is that whenever you try to code something up that specifies what is interesting, and then you optimize against that function, you get all sorts of weird pathologies that are not actually interesting. They score high according to this measure, but you realize that measure was giving you what you asked for and not what you wanted. That relates to Goodhart's law, that when a measure becomes a target, it ceases to be a good measure. An example is, intrinsically motivated algorithms, they try to find new states. Well, if you find a TV and you sit down, it will endlessly generate new states, but the robot isn't doing anything interesting after the first couple of minutes. Similarly, if you ask for an endless stream of new robotic positions, you might just get twitching, that it will always produce a new configuration, but is not doing anything really interesting. So these past approaches to hand coding what counts as interesting don't work. That relates to the quote from Justice Stewart that I mentioned. And so I argue that automatically identifying what counts as an interestingly new thing is the most important problem in open-endedness. This is maybe our grand challenge. And so I think we now actually have the beginnings of an answer in the form of foundation models. So foundation models have read the entire internet, including lots and lots of people talking about what they find interesting, but also what they find boring. They've kind of distilled this ineffable concept of what it means to be interesting into the weights of the model. And so that allows us to just ask them. They basically have common sense. You could say, would it be, I've already tried to memorize this many digits of pi. What's the next most interesting thing I could do if I wanted to learn as many interesting tasks as possible? That model is not going to suggest we're like memorizing more digits of pi. It's going to say like, maybe you should go practice calculus or learn to cook an omelet or something like that. So that leads us to this algorithm, OMNI. It stands for open-endedness via models of human notions of interestingness. And the idea is we're going to have reinforcement learning. It's going to be conditioned on tasks. And the task sampler has to create tasks that are have high learning progress. So we are learning something, but also whatever it is that we're learning is interestingly different than all the skills we already know. And we try that. For learning progress, we use some work out of my team at OpenAI. But for the model of interestingness, we just go to GPT or any foundation model, and we just ask it, basically, here's what you know how to do already. Is this interesting task? Is this task that just got proposed? Would this be an interesting thing to try to learn next? We did it in this 2D Minecraft thing and in this baby AI task. And in both cases, if you uniformly sample tasks from the space of tasks, it doesn't learn anything. There's too many tasks to learn. If you focus on learning progress, you do end up learning tasks. But if you focus on tasks that are interesting, different as you go, you actually end up doing much better. Now, this is measured against some tasks that at the outset, ahead of time, we picked. These are the kind of interesting things that you should learn to do. And then we basically let the system go and it learns a bunch of stuff. And then we measure how do they do against things that we, as humans, a priori thought would be interesting things to accomplish in this domain. So that's pretty important. We then wanted to push it even further. That was kind of it was selecting from a space of a large space of possible tasks, but we really wanted to push it to an infinitely large space of tasks. So now we're going to let it do any possible task that you could describe, such as put a toaster on top of a tea kettle on top of a plant, for example, or anything, like try to do a backflip and then fly through the window. It could try to do that. The problem is and this gets to the question that was asked to me, once you have any possible task allowed, how do you know if you have accomplished it? It's not easy to code up a simple bit of code that will tell me if I did a backflip and then flew through the window in this particular environment. So I call that a universal reward function. That's what we need. And it says if any task has been completed. For these particular experiments, we're going to basically say we can use a trick, which is we can ask GPT to write a function that will score that task too. So it has to generate the code that will measure if a task is doable. And it does limit, to some extent, the tasks that it can ask, but it allowed us to get to work. In the limit, you'd want a video model. They can just watch a video and just tell you if any task that you asked about in natural language was conducted. So in this much, much larger task space, If you do uniform sampling of tasks, it's crazy. The space of possible tasks is just enormously large. Nothing happens. If you do learning progress, you also have it doing a bunch of tasks that it is learning, but they don't learn interesting skills measured against this external set of what we consider to be kind of naturally interesting things to do in this kitchen environment. But if you run OMNI, it's slowly, the more compute you give it, it makes progress towards the goal of learning more and more kind of useful, interesting skills. It's also kind of cool to see the curriculum. It like first like goes and finds an apple, then it finds a knife, and then it ends up slicing the apple with the knife. And so it's kind of making a natural, intuitive curriculum over time. Okay, so OMNI is quite good. It has an infinite task space. It's still trapped in one kind of environment. In this case, it was this kitchen simulator. And so what we really need is this idea that I put out in my 2019 AI generating algorithm position paper. We need something that I called Darwin complete, as a nod to being Turing complete. This is a search space that has any possible environment imaginable or computable in it. And that's what we really need. So how might you get that? So the follow-up paper that Jenny did with these excellent collaborators, Jenny and Max here, is that we want to allow the system itself to create its own environment and literally create any possible environment. And what is the way that you can create environments? Well, you can write code to create them. So we now have OMNI, but with environments programmed in code. And the idea is, rather than using a specific environment that we create, it's going to come up with the code to specify the environment. It could be its own entire simulator or like a level in a video game or whatever, and the reward function, and have to make sure that it's interestingly different over time. So here are the seed environments here. We give it this environment, the code to produce this environment. We give it the code to produce this environment, and we give it the code to produce in this environment, and that's it. And then we tell the system, keep generating new interesting environments that are learnable forever. What happens? Well, the first thing it does is it makes these different platforms that go up and down. Then it goes and it says, okay, why don't I add some distractor obstacles for the agent? Then it puts some gaps between the platforms as they're going up and down. Then it puts it creates a little obstacle course that the agent has to run around. Then it starts saying, let's make a whole room with obstacles that you have to get from point A to point B in the room. Press this button to like create a plank and then walk the plank. Push down some dominoes, which it does. Do what my children love to do, which is smash a tower of blocks that one of my other children has created, etc., etc., etc. And basically, as long as we have been able to run this algorithm, it keeps generating new interesting things forever, including all sorts of wild things. So we started to create obstacle courses with moving goalposts, where I had to do a bank shot off the wall. It invented a game of dodgeball, soccer. It even made a construction site that you have to clean up, the agent has to clean up, and then a cluttered restaurant with like dishes on the table that the agent has to clean up. So I think this is getting to the point where if I had like massive amounts of compute, you might want to run this for a really long time and see what it does. You could do it with a different robot as well. You could even have the system create the code to specify the robot if you want to simultaneously evolve the robot. You could have the code specify the architecture and the algorithm. You can see all the pieces of the AI generating algorithm could now be put together with massive amounts of compute. So to conclude this little mini chapter, this OMNI chapter of the talk, we have this idea of open-endedness, but now using a human notion of interestingness as distilled into the weights of a foundation model. I think that finally allows us to enable a focus on interesting tasks, because foundation models have learned this ineffable concept from humans, and OMNI Epic allows us to do that in a Darwin complete search space. Any possible environment that you could create on a computer, this system could code up and then challenge the agent to learn in. And, you know, who knows? Maybe that's the beginnings of something that you might want to run for 1 billion years. Now, there is the question that was asked in the room that I want to address now, which is, could this really go forever? What is the bottleneck? Well, compute's one bottleneck. This stuff is very expensive to run. So we have not yet seen it run out of steam. But many people ask me, rightly so, could this thing really innovate forever? Like the foundation model that you're using, the thing to judge what is interesting, would it recognize interesting new innovations like way out in the future? And the short answer to that is we don't know. It's an empirical question. You can make arguments why it might not work. I could make them, but I think it's interesting to think about how it might work. Not that it's guaranteed to work, but it might. And that is, in my view, what counts as interesting is a function of history. So I'm a human. I know I have a good sense of what counts as interestingly new. I can read all of the papers of today and then know whether or not the thing of tomorrow counts as interesting. And that function, I think I could port way out into new spaces. For example, if I woke you up in the year 3000, you would be blown away by the technology that is there. But once you acclimate to the technology and you learn what is possible, my guess is you would recognize the next interesting innovation, and then the next, and then the next, and then the next. Because all you need to do is learn enough about that stuff to then bring your model of interestingness to bear. And for all I know, language models might be able to do that. If they don't, then we need to figure out some fine-tuning thing, and then there's a lot of research to be done on how to do that. But who knows? Maybe this concept generalizes really, really, really far. Okay. I want to keep going with a couple other papers, but if you guys want to stop and ask questions about that, we can do that. It just means not getting through some of the other chapters.
Okay, there are questions.
All right, let's do it.
I have a very general question. I want to ask, what's your view on explicit versus implicit gradient? I guess the reason I'm asking is because in the paper, we're asking GPT to evaluate interestingness, which is a very important metric that you want to improve upon or optimize for. So in that way, asking GPT is kind of implicitly getting guidance to which direction to go next. And I'm wondering and I've seen a lot of paper we read in this class use this approach where there's no explicit gradient defined that we want to optimize for. So I'm wondering what are your thoughts on using the two? Does that make sense?
So that's a good question. I think in general, basically, if you can get a gradient, it's really helpful and often makes things more efficient. But it's not required. If you can't get a gradient, there are other techniques you can use, like RL reinforcement learning, often policy gradients, or even evolutionary algorithms, other kinds of search that you can use to get and to still make progress. So it can be helpful. I think the harder thing is how trustworthy is it? If you start optimizing against it, do you end up with pathologies? Maybe the hard part is not getting the gradient, but do I have the right gradient?
More questions? No more questions for now.
All right, cool. So let's move on. So the next thing I want to mention is something that this is work that I did at OpenAI with a wonderful team that you can see here. And this is called video pre-training, or VPT. And the idea is that, one of the things, so somebody asked, what are the bottlenecks? As I mentioned, computer is a huge bottleneck. And why is computer a huge bottleneck? Well, one of the main reasons why compute is such a huge bottleneck is because currently our learning algorithms, especially when you're doing reinforcement learning, they're very sample inefficient. Exploration is too hard. As I mentioned, just throw this Montezuma's Revenge game at current RL, and unless you take Go Explore or an algorithm like that off the shelf, then it's pretty much hosed and it will never learn. And that's a very simple game. Imagine a much more complicated game like you might see in the real world or in a very complicated video game. So exploration, the ability to learn the next challenge, is a huge tax. So even if you generate interesting problems forever, if those problems themselves are really, really difficult for the agent to learn, then you have to pay this tax. Now, in theory, learning progress and meta learning can overcome this, but it might take a really, really long time. So can we bootstrap the process? Well, Josh Tenenbaum asked me a form of this question when he said, can we make your AI generating algorithms without a planet-sized computer? My answer is yes. And the answer, the reason is, to borrow from Newton, that AI sees further by standing on the shoulders of giant human data sets. So as we know, AI is catalyzed by training on human data. That's basically the lesson of GPT. So when you want an embodied agent to solve a complex task in a physical space, you can go to the internet. The last great repository of data is video on the internet. And there's tons and tons of videos of people doing things and solving problems. And you could watch them all and then start your agent out basically having already read and learned about everything that humans know how to do. We chose the example domain of Minecraft, but you could have chosen a domain like using a computer, for example. And so the problem is that these videos that you find online, they don't have actions. They're perfectly fine if you want to learn something like Sora that will generate the next frame and the next frame and the next frame. But Sora does not tell you what action to take at every frame in the video. And that's because if you just download a video from YouTube, you don't get to see what was the agent doing on their their keyboard, their mouse, or with their PlayStation controller as they were producing the video that I am currently watching. So for things like text and music and images, you always get the next label for free, but with a video where you're trying to infer actions, you don't. So the solution we came up with is to train what we called an inverse dynamics model. That wasn't our term, that had pre-existed, but it's what we were doing. We basically show it some video. We show it both the past and the future. This is a separate model, what we call the IDM, the inverse dynamics model. And the job of this model is to look at the past and the future and say what action must have taken place at this time step. So here you see that the agent has jumped, and so the model can say, oh, you must have hit the jump button. And that's a pretty easy problem, is to infer what action must have been taken. So to do that, we're going to go, once you have that model, you could go label the entire internet, because now you can infer all the actions that have been taken, and now you have tons of data. So to get this model, we paid some contractors to play Minecraft, recorded the actions that they were taken while they were acting, trained the IDM to guess what those actions were without having access to them. We then went and labeled years worth of people playing Minecraft online, trained a 500 million parameter transformer, and zero shot coming out of pre-training, the thing with massive amounts of data, and only with massive amounts of data, the thing starts to learn how to do things that take humans about 2 minutes and like 2,000 to 3,000 actions, such as making a crafting table in this game. And here you can see some examples of this. This is also after a little bit of supervised fine-tuning, but I want you to pay specific attention to this video on the right. I'm going to start it again. So imagine you drop your agent in this village here. It knows how to systematically explore the village. It has the skills to move around, to open doors, examine chests, go upstairs, check beds, things like that. If you put an agent like that in a new environment, it's going to be much more efficient to learn than an agent that's just pressing buttons randomly and hoping it eventually gets a reward. And we put that hypothesis to the test with reinforcement learning. So here, at the time, there was kind of an open challenge in the field of having RL learn to get a diamond tool in Minecraft. This takes humans about 24,000 actions in over 20 minutes, a skilled human. And so we're just going to reward every milestone along this little tech tree here. And what we found is that if you don't do pre-training, if you don't do VPT, it's impossible with RL to learn how to do this task. But with pre-training, then you slowly can learn each task, each rung of this ladder, and get to the top and eventually do this task that, again, takes a skilled human over 24,000 actions and 20 minutes of behavior. Which I think is pretty impressive. So I'm not going to show you this whole video here, but it really gets good at using a computer. It's using the mouse and the keyboards, and it's only looking at pixels, and it knows how to drag and drop things, etc. And when we did this, we knew that the long-term goal of this research was to ultimately get to computer using agents. And just last week, you saw OpenAI put out what I consider to be like the descendant of this project, which is Operator, where they trained a model to go use a computer to do whatever you want to, whatever you could do on your computer. And so 2.5 years after we did this work and mentioned that this was a step towards computer using agents, OpenAI released a product where it is doing that, in an actual product release. So congrats to them. So to conclude the VPT chapter of the talk, pre-training enables learning really hard exploration tasks efficiently, and that can seed our process of creating agents that could go and learn forever, paired with the other ideas in this talk. I'm currently at DeepMind, as Azalea mentioned, and a project that we have there called Sima actually did something which is kind of like this project on steroids. We trained an agent in 12 environments, really complicated 3D environments, and then we showed that it could become a generalist agent that you could ask it to do kind of whatever you want it to do. And amazingly, when you transfer that agent to a 13th entirely new video game it has never seen before, it generalizes almost as well as if you just trained on data from that environment. So we're really starting to see transfer to wildly out of distribution environments occur once we throw a lot of compute and a rich diversity of environments at these agents. Another project out of DeepMind that I want to mention is this project called Genie, because it really also gets to this pillar 3 of AI generating algorithms, which is automatically generating environments. So this also is going to stand on the shoulders of giant human data sets. It's going to go and watch a lot of online videos of like video games, and then be able to create a generative model of video games. But unlike a video model like Sora, which will just generate endless frames, this is playable. It learns how to respond to the actions that you give it. And so it basically is a generative model of a video game. And you give it any picture you want. So in this video, like here's a picture. And then it will produce like a video game that looks like that this thing looks like a screenshot from, which is pretty fun. In fact, it's so cool that my children wanted to play with it. And so we took pictures my children drew, we gave it to Genie, and it basically animated them. So we now are getting to the point where we have models where a child could sketch a world with crayons and then step into that world and play it, like walk around in their imaginative world, which is pretty cool. You could use it for training robots. So all of this is synthetic data produced by the system from a single picture, which is pretty cool. And just a couple of weeks ago, actually maybe it's months ago now, we put out Genie 2, which is the second model. Basically the same idea, some technical differences that I'm not going to get into, but just scaled up. And as we all know, scale works wonders. And so now we have 3-dimensional worlds. All of these are automatically generated from a text prompt. Text prompt produces an image from an image generator, and then we produce an entire interactive, playable world, like a video game, from that picture. So here, for example, is the same starting image, and this is a text conditional agent. So we can say go through the left door, and it goes through the left door and then imagines what's through that door. Same thing with the center door, and same thing with the right door. And this is actually the Sima agent, which I told you about, in the Genie created world. So we're seeing a policy that was trained on human data, and a world model, like an environment generator that was trained on human data. And so this is what I'm talking about when I say that we're in a new era where open-ended algorithms are being catalyzed by modern generative AI. Here are more samples. All of these are pretty fun and pretty cool. In the top, you can see different actions being taken in the same environment. In the bottom, just really rich physics, blowing up barrels, popping balloons with a katana, driving a boat around. All of it just imagined by a big neural net. Fun fact, in 2019, when I wrote the AI generating algorithms paper at Uber, I thought to myself, what is a Darwin complete search space? Like I can theoretically imagine it, but like what might actually instantiate it? And I was like, well, it's crazy, but the only thing I could think of is a neural net. Imagine if you had a giant neural net and you just give it the current observation and an action, and it generates the next observation, and then it could produce anything. And at the time, it sounded so crazy to even think that I almost didn't put it in the paper because I thought people would like think that I'm nuts, and I'd like, my career would be at risk. And how many years later? 5 years later, and we have Genie 2 in front of us. So you have to trust your rational brain when forecasting an AI, not your emotional brain, I think. Okay, now I was invited to talk about 2 papers. Specifically, and I decided to share a much bigger arc of work so I could situate those 2 papers in the broader context of work. I hope you don't mind. But we've now arrived at the 2 papers that I was originally asked to talk about, which are the automated design of agentic systems and then the AI scientists. So these are the next 2 things I want to talk about. So this work is done by 2 awesome people in my lab at UBC who are actually, I believe, on the call, Sunren and Song. So they're here to answer questions if we have technical questions I don't know the answers to. They did a wonderful job. So the basic idea behind this work, the automated design of agentic systems, is that, as you well know, because it's the theme of your course, the old school way to interact with a LLM was like prompt it and get your answer. But nowadays we've moved way beyond that. And so we need a name for whatever this new thing is. This new thing is you have an LLM at the core. It might be interacting with tools like calling Semantic Scholar or Google or going to Twitter. It might have a memory bank or a scratch pad. It might interact with people if it needs to. It could have its own goals. It could have planning, reasoning, chain of thought. It might be able to take other sorts of actions. It might even have other agents like a critique agent, a reviewer agent, a skeptic, whoever that it creates or somebody else creates. And there's some complicated workflow of like, what is the flow of information and action through this system? So this whole big complicated mess, we are calling an agentic system. Some people just call it an agent, but for me, like an agent is like an RL agent, like operating in an environment like Dota or StarCraft or something. So this feels like it needs a new name. So we're calling this an agentic system. And if you look out into the literature, I don't expect you to actually be able to read this. These are some of the workflows or the blueprints of current state-of-the-art agentic systems. And what I really wanted to show you is that they're very complicated. And currently, people are manually designing them, and they work better than just an LLM. And there's a lot of manual work to create these things. But as you can imagine from the way I'm setting this up, the AI generating algorithms philosophy is, hey, let's like ultimately manually designed pipelines are replaced by entirely learned pipelines. So why don't we apply that to agentic systems itself? And so Ren was the one who really connected the dots on having that theory and that idea that let's go, it's like we should try this. And so what we're going to do is we're going to use the ideas I've been talking about in this talk. Quality diversity algorithms, open-ended algorithms, using a sense of interestingness coming out of language models like OMNI, and we're going to try to use these principles to automatically design agentic systems. Now, we're not the first people to try to automatically design agentic systems. Here are two references, but I think we're the first people to do it in code. And the reason why that's important is because code, in our case, Python, is Turing complete. And so it can create any possible agentic system. It's really a really broad and expressive search space. And so all we do is basically say we want to endlessly provide interesting and or good agentic systems and add them to an archive. So the name ADAS refers to the space, the class of problems when you try to automatically design agentic systems. Sorry, going backwards. And then we also want to introduce a specific instance in ADAS called meta agent search, where we're doing things in code. And so the way the meta agent search is going to work is it's going to use the principles of open-endedness and AIGAs and quality diversity. And it's going to say, hey, we're going to have an archive that over time is going to increasingly have interestingly different agentic systems in it. And we're going to look at that archive to generate the next interesting one and the next interesting one and the next interesting one. It doesn't necessarily have to be higher performing. If it's either interesting or high performing, we'll add it to the mix. And that's what this high level diagram shows. So we have a meta agent whose job it is to look at the archive and make the next new interesting agentic system. And it can keep trying, looking at error logs and messages and whatever. It itself is an agentic system, producing a new agentic system for a particular problem. And if it's interesting or different, we'll add it to the archive and we'll repeat. And here is a look at that meta agent. It basically has the archive. It has the description of the target domain. It has instructions for how it should probably go. Like it might have chain of thought, like make sure you think really carefully, think out loud about the agentic system you're designing. Maybe you reflect on it, etc. And then eventually it produces the next interesting agent, and that will go into the archive. And so the first thing we applied it to is a simplified version of the ARC challenge. And there's all these state-of-the-art hand-designed agentic systems. We tried them all, and here are their performances. And what you can see is the meta agent search starts out way worse, but slowly over time, it's coming up with better and better ideas. And eventually it gets much, much higher performance on this particular problem. And again, our only bottleneck here is compute. If you gave me, millions of dollars, I'd love to run this longer and see how good things get. But if we take this final best agent and we look at it, here's kind of a high level schematic of its workflow. And you can see it's got a lot of cool innovations. It has, it creates its own critic, it refines things, it has a panel of experts, and that it gives it the diverse amounts of reviews and opinions that it then uses and responds to, et cetera, et cetera. So it came up with some pretty cool stuff. We also tried it on these reasoning and math tasks. So here's some reading and math tasks, and we compared it to all these state-of-the-art agents. And what we find is that it performs really well on all of these different domains. And what really surprised us, we were hoping this would work, but we didn't expect it, is that it even produces agentic systems that generalize well. So since we're searching on an agentic system for this particular math challenge, you might expect that it's overfit to this particular math challenge and it wouldn't generalize to new math challenges, but that's not true. It actually does really well on these new math challenges. It even does well on non-math challenges and is effectively state-of-the-art when it's generalizing out of distribution to versus hand-coded agentic systems, which I think is pretty cool. I want to mention this particular work had a lot of unique safety challenges. So I want to mention that we did follow a lot of best practices here. I do think if you're automatically executing AI generated code, you want to be really careful. And so we use containers. We monitored the process to make sure nothing unsafe was happening. We didn't observe anything unsafe happening, but we monitored it. But even then, that's not enough. As these systems get more powerful, we want better and better AI safety methods, including aligning the agent throughout search so it never tries something dangerous. Like it doesn't even want to try to do that. So maybe ideas like constitutional AI or other new ideas we need to invent. So I think there's just a lot of exciting future AI safety work specifically on open-endedness and in ADAS in particular, and in general in self-improving AI. There's lots of future work you could do here. Of course, you're probably all wondering, since you have a meta agent that is creating the next agent and the next agent and the next agent, could it improve itself, right? That's a natural question. And so we are actually currently working on that. So we'll, it's very hard, but we think it is doable, and that's why we're pursuing it right now. So all of this is open source in case you want to play. So to conclude the ADAS chapter of the talk, I've talked about automatic design of agentic systems, which is a new area of AI, I think a new subfield that's growing, where you're switching from handcrafting agentic systems to automatically learning them. They tend to be higher performing and are automatically produced, which is quite nice. I think that's in line with the main trend that we've seen so many times in AI over decades now. And our particular search is the first one to do that in code space, and it works quite well, and the agents end up transferable. So if you don't mind, I'd like to just do the AI scientist first, and then I think I can just wrap up and take questions. I'm going to skip the last chapter of the talk. So I'll press right on to AI scientist. So you might naturally say, okay, that was, or we thought, hey, agentic systems are really cool, but that's not the whole enchilada. Like, is AI now ready to start doing science itself, to automate the process of all scientific discovery, to basically act like human scientific communities? So this wonderful team of people from our lab, led by Song, but he's the leader from our lab. There are leaders from other places, Chris and Robert here, pushed really hard, did great work on this project. So the idea here is that science is the ultimate open-ended domain. And can we automate all of science? And we think the answer here is yes. We chose as the first domain machine learning because in machine learning, the computer experiment is the real world. It's not a simulation of the real world. And so it's kind of the low-hanging fruit to do this research fast. We also know the domain well, so we didn't need to ramp up on some arbitrary domain. But I think you could apply this same work to other domains, like if you had an automated chemistry lab or something. So the most wild thing about the AI scientist is that it does the entire scientific pipeline. It comes up with its own ideas. It comes up with the plan for what experiments to try that will test our hypotheses. What should the controls and baselines be? What should the code look like to run those experiments? Then it creates that code. It then runs the experiments, analyzes and visualizes the results of those experiments, writes an entire scientific manuscript, conducts peer review on itself, its own papers, and then if it thinks they're good or not, it kind of reports all of it in an open review style thing that goes into an archive, and then it reads the archive of the discoveries it has made so far to then produce the next generation of papers and the next paper and the next paper and the next paper. That's what it's doing at a high level. In a little bit more detail, it comes up with it. You have like the LLM comes up with a plan. Then it can go use a tool. It goes and checks Semantic Scholar to make sure that its idea hasn't been done by humans. It then scores how novel and interesting is this idea. We give it a template for a particular type of experiment. Like if you're working on grokking in machine learning, we give it like a base set of code that it can run some simple experiments. It will then modify that code to implement its unique experiment it's working on in this paper, run that experiment, get the data, look at logs, revise the plan, revise the code, etc. Ultimately, get the data in plots. It then has a LaTeX template for like a NeurIPS paper. It fills in that template, writes the paper. It has lots of loops where it checks like how good is my paper, is the writing good, is the logic good, am I doing what I should do I have all the right references, etc. And then ultimately we actually created a reviewer that reviews the paper and scores it, and then the loop goes back and we close that loop. So a couple of quick results. One is that the reviewer we made is, at least according to these metrics, it's not that easy to score them, but it basically is about as reliable as humans at performing the review process, which is pretty cool. It's also just wild to see the papers that it generates. Like, you can just sit down and read an entire paper. And if I didn't tell you it was AI generated, in some cases, you probably wouldn't know or notice. If you look at the actual scores, according to our reviewer of the papers it generates, it's, usually about a 3 or a 4, which is kind of like a reject or, weak reject. Sometimes it produces 5s, which is borderline. And in rare cases, so far, we're producing papers that it thinks should be accepted at a, top tier machine learning conference. So that's pretty wild. One thing that I thought blew my mind is one of the better papers that it generated that I read and I liked. I thought it was a really creative idea. It basically, in a nutshell, it's like, how do we study grokking and machine learning? How might we predict grokking? Well, maybe grokking happens around the same time as a really sharp decrease in the compressibility, the minimum description length of a neural net. So if we can measure the minimum description length, maybe that will predict grokking. And I was like, that's really cool, but how are you going to measure minimum description length? And it came up with a way to do that, and it did all the experiments. And so I was like, that's a really, really cool idea. I didn't think it actually, in the end, executed it well. I would have rejected the paper, but I thought the idea was very nice. And the proposed way that it was going to test the idea was nice. And then literally a couple weeks later, a team did that work and put that work on the internet. Now, they independently thought of it, and they thought of it ahead of time. But I just think it's really cool that the AI scientist was standing on the same shoulders as humans and kind of came up with the next idea. The human team executed it better, and their paper looks way better than ours, but same basic idea. So it shows you that this AI scientist version 1 is already kind of on the scent of how to be able to do really interesting science. Once again, we did containerization here. We watermark all papers for transparency. I think there's a lot more work to do in AI safety for science. Like, we don't want it to do dangerous experiments. Like, I don't want it to do gain of function research on COVID. We want it to refuse unethical science. Like, there's all sorts of that. And we have to think about how this is going to affect our community. But to conclude the AI scientist work, we're showing that the entire process can already be automated. It's far from perfect right now, but as everyone in our field is probably very familiar, if you can do something pretty poorly in AI right now, it's only going to be a couple of years before you can do it really, really, really well. And so, what does AI science look like with a decade of progress, or a lot less? I'm not going to talk about the future work here. I want to get to a little bit of Q&A. I was going to talk about this thought cloning work. I'm going to have to skip that. I just want to do my conclusion slides and then take questions. So the overall conclusions here, I hope that I've sparked the idea that quality diversity algorithms are interesting. They explore well, they create and collect stepping stones, they harness this idea of goal switching, and they invent effective counterintuitive curricula. I've introduced open-ended algorithms where the goal is to literally innovate forever, and like natural evolution and human culture. AI-generated algorithms are basically applying that to the production of AGI itself. I think it's likely the fastest path to AI. And it's just really an amazing time to work on open-endedness and AIGAs because of language models. So via foundation models, open-ended agents get to stand on the shoulders of giant human data sets. I think that speeds everything up and makes it easier, both in terms of environments like Genie and agents like VPT and Sima, because you can just kind of skip to the interesting part. And then you have ideas like OMNI, where we can finally pursue what is interesting in a Darwin complete search space, because the model itself knows what is interesting. And that then leads us to the AI scientist and meta agent search, where the same set of exciting ideas can be applied to agents and science itself. And I didn't get to talk about thought cloning. So that's the set of ideas I wanted to share with you. So thank you very much for listening, and I'm happy to take any questions you have for as long as you want.
Sounds good. Thank you so much for a great talk, and thank you for including all this kind of really deep topics.
Awesome. Thank you, everyone. And thanks again to you two for inviting me. It was great to be here.
Yeah, and hope we get to talk soon about
I would like
these
that.
topics. All right. Thank you. Bye.